Uncertainty quantification in image retrieval is crucial for downstream decisions. My name is Frederick Warburg, and I will present the Bayesian triplet loss, which is a probabilistic equivalent of the triplet loss, and which produces state-of-the-art uncertainty quantification for image retrieval. In the image retrieval pipeline, a user queries an image, and the goal of the system is to return the k most similar images from a large database. Images are embedded as compact vector representations, either using handcrafted features or convolutional neural networks. The vector representations are constructed such that similar items are close and dissimilar items are far apart in latent space. Recently, learned image embeddings have shown superior performance to handcrafted ones. The triplet loss is often used to train these image embeddings. This loss operates in triplets with 2 images from the same class and 1 image from a different class. It seeks to make the distance between an anchor and a positive smaller than the distance between the anchor and the negative, plus a margin. We'll refer to this as the triplet constraint. In contrast to pairwise losses, like the contrastive loss, the triplet constraint allows more flexibility to model interclass similarities for different classes. However, the triplet loss comes with no notion of uncertainty. In contrast to the triplet loss, we model embeddings as distributions rather than points, such that data uncertainty is propagated to retrieval. We propose a likelihood that matches the triplet constraint and evaluates the probability of an anchor being closer to a positive than a negative. Our method can be seen as the probabilistic equivalent of the traditional triplet loss. We define our likelihood for all triplets in the dataset. We note that the triplet labels can take 3 values with respectively 1, 2, or 3 images from the same class. The traditional triplet loss ignores the situations where all images are from the same or different classes, as these situations are not informative. Making a similar modeling choice, our likelihood reduces to only consider triplets with 1 pair. We then define P as the probability of an anchor being closer to a positive than a negative, mirroring the triplet loss. I now proceed to derive an explicit expression for this probability. We first rearrange the probability and seek to find the density of tau. The squared distance between 2 normally distributed random variables follows a scaled non-central chi-square distribution. Our likelihood is a linear combination of 2 such terms which does not have a known density, and therefore we resort to approximations. We choose a Gaussian approximation and show in the paper that this approximation is very accurate even for low dimensions. We can now analytically derive the mean and variance of our Gaussian approximation. The expressions for the mean and the variance might look a bit scary. However, the equations only depend on the mean and the variance of respectively the anchor and the positive and the negative stochastic embeddings. We therefore ask our network to predict a per-image mean and variance. Our model is a standard convolutional network with 2 heads, one for predicting the mean and the other to predict the variance. By optimizing the proposed likelihood, we can learn reliable uncertainty estimates while matching the predictive performance of the traditional triplet loss. Having now derived a likelihood that can be used to efficiently optimize the distribution of image embeddings, we can add priors and perform traditional Bayesian inference. Lastly, we note that our likelihood is a CDF rather than a more traditional EDF. Our method provides state-of-the-art uncertainty estimates while matching the predictive performance of the triplet loss. It associates high uncertainty to hard examples, like the birds that blend into the background and are hardly discernible. We show on the large-scale place recognition dataset, MLS, that our model can provide reliable uncertainties for place recognition. We see that high uncertainty is associated with challenging places with harsh sunlight, blur, and ambiguous tunnels, while low uncertainty is associated with buildings with unique architectural characteristics. In conclusion, we present the Bayesian triplet loss, which mirrors the traditional triplet loss. We show that we are able to learn reliable uncertainties in latent space while achieving comparable predictive performance to state-of-the-art. For more information, please see our paper or visit the project website.